arrows for these two ways. Finally, I must tell you what the arrow is for the net result. When things can happen in alternative ways, you do what we call add the arrows, and it doesn't mean anything. How do you add arrows? I know how to add numbers. How do you add arrows? The rule for adding arrows is the following. You simply put one arrow head on the tail of the other. If I wanted to add these two arrows, I would do it as follows. This is the first arrow. Let's say that's 1 and that's 2. That's the first arrow. And then I just draw the second arrow off from the first one. Okay? It's exactly parallel. So drawing the same, but it's centered, is moved to there, right? You tie one onto the other, head to tail. And the result is supposed to be the sum. The adding is this net arrow that you would get from where you started to where you ended. A way of thinking of it that's rather nice is to think of each arrow as indicating the direction of a step to be taken. We take a step on this plane this way, and then we take a step that way, and we say, where did we actually move? We could have done it all in one step, this one. So this is the one step which is equivalent to the succession of the other steps. Adding means putting together steps, thinking of these arrows as steps that you do in succession. This added arrow is the final result for the chance of a reflection. The square of this arrow determines the probability of reflection. I have to have erased the blackboard because I haven't got room. So I'm reconstructing here on a smaller scale a diagram that we had made earlier, which was the reflection as a function of thickness, which I'm trying to explain. And this is up to 16%, remember? Averaged 8% and started at 0. Now let me explain why it's true, if I follow these dippy rules.
This must require an incredible accuracy of measurement.
Not particularly. Not this one.
I mean, timing here.
Oh, no, but you see the timing is automatically taken care of by just the distances. The timing is very short. But
The distance.
well, we have to have the distances good, yes. But you see, if this is put in a fixed position, it's a definite distance, whatever it is. We don't actually have to know exactly how this is turned. We have to know the relative turn of this and that. That's a nice point. Suppose that I made a mistake in that distance. Well, I moved the photomultiplier a little bit further away. Then this arrow here, the red's going to indicate what I would calculate if I had a little further away the photomultiplier. Then this arrow would have turned a little further, right? And this arrow would have turned a little further, always in the same direction. Yes? And now I want to add these two together, which I will do, again, just like I turned blue to black, I'll turn red to orange. I'm going to add the red ones. It's a new problem. He moved the photomultiplier on me, and I'm doing it over. So I make this step, and then I make this step. Okay? And then I get the final result, which we'll draw in purple, that corresponds to the other green one there. And it looks like it's the same size, doesn't it? Maybe I cheated. I'm good at drawing. But it is exactly the same size, because if you think about it a little while, since you turn this arrow by a certain extra angle and this one by the same amount extra, because when you move the photomultiplier, the extra time is the same for both, the extra time. So the extra turn is the same for both. It's the same as just turning both arrows together, which is simply turning this diagram. But turning this thing doesn't change its length. And the probability that we're calculating depends only on the length. It's the square of the length. It doesn't depend on the direction.
Can't you get that directly from the glass thickness? From the glass to the glass?
Absolutely. You mean that this angle here, this delay? Yes, yes, and we're going to do that right now. And that's exactly right. That's why you don't need the accurate measurement that you were talking about. You don't really need that distance to get this probability, because only the thickness of the glass is important in computing the length of this arrow. The direction of this arrow does in fact depend upon exactly where the photomultiplier is, but it doesn't affect the probability that you'll get a count, because the count is measured by the length of this arrow squared. Right?
So it's the scalar, not the vector.
No, because I need this. Sometimes I might have 3 surfaces and I may not have a photomultiplier there, but when I get there I have another surface that a light reflects from and so on, so let me have it with arrows. But when you finally want the probability for something, then at the end you square the arrow. For this application, it's the same answer here as here. Okay? But if I had, instead of putting a photomultiplier there, I had put another surface there, then the exact location of it becomes very important. Okay? It has another reflection with another photomultiplier somewhere else. It would be a different problem. But let's just do this easy problem first. Let me explain why this result would occur if these rules were right. Why, if we count the beans by this way, we get this result. Let me show you, all right? He's already seen it, as a matter of fact, from his questions. Suppose that we would do the problem over again, not this time moving the photomultiplier, which was, we found out was an effect, didn't change anything. So I'm going to erase the red and orange to get space. I'm now going to ask you to think of another circumstance in which I change the thickness of the glass by increasing it, let us say, a little bit. So I do the experiment over again, and now my red and orange and all that's going to correspond to thicker glass. To make it very clear, I was going to do it over again in which the back end of the glass is here instead of where it was before. What happens? The amplitude, well, I mean the arrows are called amplitudes, so I may sometimes say amplitude instead of arrow. It's just a word, right? We can have any word we want, like it says in Lewis and Carroll. Lewis Carroll, I mean. The reflection from the amplitude corresponding to reflection from the first surface is this arrow turned by the distance to the photomultiplier, which is that. Changing the position of the second surface has no effect on that arrow or that amplitude. Instead, however, the one which went down to the new surface and back is changed. Why? Because it has to go further now. And in going further, it will be turned more. So it will be in this position instead of where it was before. This corresponds to turned more because it's thicker. This is the one that's thicker. All right? Now we have to put these two arrows together, and I'll do that over here. The black one from the old one, which is the same as it was before, straight up and down. That happened accidentally for my drawing. And then this red one, which is now, I'll draw in red again. I don't want to change all the colors all the time. Out this way more, right? You can see it. I'm trying to draw it parallel. Just like I drew this black one parallel, I'm drawing that one. I'm making the two steps again. But this is the first step this time, and this is the second step for the new experiment. So there's the first step and second step for the new experiment. The result in this new case is the new green arrow. I got so many colors and have so many possibilities, it would be sensible to put the right color caps back on them in case I want to get the right color. Right? But I can't resist having every color in the rainbow on this diagram, but I don't know that it helps any. At any rate, we have this green arrow here. You'll notice it's longer. And why is it longer? Because this angle opening is greater. So it's longer, and being longer, its square is greater. And the probability of reflection then in the new situation should be larger. The probability of reflection will depend upon the thickness of the glass. And in this particular example, this may have been the first point, and this may be the second point. That is, it increased as we increased the thickness. That's how it works. Simple as long as you believe all this, that it'll work. I mean, yes, it is simple. It's just drawing arrows.
Configuration of the arrows to once again produce the thickness, where you keep increasing the thickness till you get zero reflection.
We'll see that in just a second. I just want to see if there's any other question. I'll answer that. We're going to do all the different thicknesses and get this whole curve now.
But that's exactly what the wave theory does.
Of course, because the wave theory gives the right answer too. But the wave theory doesn't give the counts. It doesn't calculate probabilities. This is for calculating probabilities.
You just rename the ordinate. You call it, instead of reflectance, probability of reflection.
It's not just a name, because when we measure probabilities. We measure average rates. We can't get a quarter of a photon. Yes, the mathematics is exactly the same as the wave, because it's very simple mathematics. But it doesn't mean the wave theory is right, because it predicts wrong things about the photomultipliers, for example, that it's counting, that it's chance. That's a very important difference. It's not the photon. The wave theory would have the waves there weak at the photomultiplier. But what the wave is, what is it? It's supposed to be energy. No, it's probability. A wave of probability? Yes, that's what. Okay?
No, I mean,
It doesn't have the dual slit right now.
I mean,
We have what you call the dual slit. He knows too much, see?
so the problem is,
We have to undo some of your lumber that we talked about.
so how does it happen if the two photons go up?
There's no two photons.
Well, I mean, the
There's
particle,
one photon.
and then they hit together, and that is,
There's no two photons. There's one photon. And it's either there or there. And we're trying to find out the chance it's here and the chance it's there. That's very important. I want you to get used to it.
I know, but I mean, it still is not,
The same mathematics is the wave equation. The mathematics is the same, but instead of calculating what you call the intensity, you're computing the probability of finding a photon. The fact that you made this change of interpretation means that the pictures of the waves is physically incorrect. Okay, so we remove the picture and just make the calculation. That's what happened. We're not going to change the calculation because the other numbers were right.
In the direction of flight, how long is a photon in terms of wavelength?
In this particular example, when it's monochromatic, it's infinitely long, but that kind of question is the kind of question we were talking about. If you try to make the model too correct, it isn't going to be right for some other question. Just sit down, just follow the arrows, and then you'll get everything right.
How could it be an infinite length? It would then be an infinite duration.
That's right. And if it isn't infinite duration, it's not perfectly monochromatic. But if it's nearly monochromatic,
Infinite cube.
these are irrelevancies, please. Okay? They're not really irrelevancies in the greatest delicacy, but everybody isn't up to your level of worrying about this particular problem, which is not...
Worrying about the duration of the excitation of the photomultiplier by one photon.
I know. It's an unnecessary complication to worry about that here at the present time. Okay?
Yes, it was.
Okay, fine. What I would like to do now is get this whole curve from this to see how it really works. So let's start by taking the case that the glass is very, very thin. Very thin. Then the two times are the same. Let us keep the photomultiplier here and the front surface exactly here, so that in every example the front surface arrow is this one. And now let's figure out what the back surface arrow is in different cases. And we'll find these pictures coming out like this. I should have used a different color here so you'd know this was the back surface arrow, okay? Here's our front surface arrow. I'll make it larger so you can see it better. Shouldn't have done that. I should have left the scale exactly the same. Yes, I shall do that. It's not, we change too many things, you get mixed up, and there's no need to change it. There's the first arrow. That's supposed to be that one. Now on top of that one, I have to add, by the other step, the second one. Let me draw the second one. This was a small thickness. This was thicker, some thickness. We'll call this thick, thicker, and very thin. Where's very thin? We noticed that this was very close to here. They both turn the same amount. And since they started opposite, very thin would be here. That would be where it would be for very thin. I'm drawing them all on top of each other. Of course, they're all separate calculations for separate experiments, and it's a little confusing. So let's just draw it all over again for the case that it's very thin. This would look like this. Same again. This one, however, would be exactly opposite. Why? Because if it's zero thickness, there's no difference in time for the front surface and the back surface. Therefore, they both turned around 1.5 billion rotations. This is a half a rotation extra net, and this is a half a rotation extra net, therefore upside down. Now let's put these two steps together. First, we have the first step for the first arrow, and now we have the second step for the second arrow, which is a step back. Although I've drawn it to one side so that you can see it, it should be tied right onto there. And where do we end up? We end up right here. So let me draw it very carefully. Actually, I made it for the case that there's a tiny thickness so you can see it. Then you see that the green arrow is virtually nothing. In fact, it is zero. If it was exactly opposite, the net result of making a forward step followed by a backward step is to bring you right back where you were. There's no net motion. And therefore, there's no probability of getting a reflection. That's why a very thin piece, that's in consonance with the experiment. It says that a very thin layer gives nothing. Now, okay, now we keep on going, and we try to imagine what happens as it gets thicker. All that's happening is that this arrow goes around and comes to here and then goes back down and goes around and so on relative to the first one. So you answered your question. You imagine what happens if you take an arrow here and then for different thicknesses, and I'm going to draw it all for a succession. I'm now going to draw the result for 16 experiments in which I go here, 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 here with different thicknesses, okay? The 16 results look like this. Maybe it isn't going to come out 16, huh? That's no thickness. There's a little thicker. A little more time, the case we drew before. Still thicker. These are not straight lines, unfortunately. They should be. They're a little thicker, a little thicker, a little thicker, a little thicker. That's more turn, right? These are the way these things come until finally, when the thickness is just right, it's turned one whole extra revolution because of the extra time. Then it's back to this case, and it keeps going around. And how long is the green arrow? Well, the green arrow starts at 0, and then it gets a little bigger, and it gets bigger, it gets bigger for the different cases. And finally, it's way up this way. That's the biggest it's ever going to get. Then it comes down again. There's a bump, right? And how high is it at the biggest? You may have forgotten, the original length was 1/5. And this is obviously 2/5. And when you square 2/5, 2/5 is hard to square for anybody. It's 4/25, which is equal to 16/100ths. Or another way, 2/5 is 4/10. This is 2/10. Squaring it is 4/100ths, which is 4%. Twice it is 4/10. Squaring is 16/100ths, which is 16%, which is okay. And that's how it works. It goes up to 16 and comes down and so forth, depending upon how thick the glass is. And this will keep on going as you keep on making the glass thicker and thicker. It's been measured to, I said, something like tens or hundreds of millions of rotations.
Is this independent of the index of refraction of the glass?
No. The time to light to go through glass is different than the time to go through air. It goes through the glass slower and takes longer to go the same distance as it would for air. So that when I calculate this turn, I have to allow that when I'm calculating this extra time, I must be careful to realize that it's not going at the full speed in the glass, but slower. So that's just to change those angles, but doesn't change the result that I got in the picture. Okay?
That's why you said earlier that you should pay attention to the time rather than the distance.
No, I just like to pay attention to the time rather than... Well, no, it's okay. It's not why I said it. Yeah, okay, why I said it. If you pay attention to the time, then you say the rule is for time, and allow that the light goes at a different speed through the glass, that explains it. Okay? Later on, if we get there, don't know if we can make it, but I will go further. I will explain why light goes at a different speed through the glass. I will actually improve this thing. I'll give you more details of how this calculation actually goes. I've cheated a certain bit because this is a result of a more complicated calculation that determines that this is 1/5. It's a result of a more complicated calculation with arrows that determines as you go through glass the speed at which you're supposed to rotate is different, and so forth. These I haven't included, but I made it suppose a certain number of things. But those things also can be explained by a finer analysis of the arrows, all right? Including the minus sign for the back surface. Yes, I'll explain. All those will be explained, I hope, if we get there, by a finer set of rules, a more detailed set. We'll just take these as properties of glass at the moment.
Well, isn't it still better to use the analogy that, you know, you're traveling?
Yes.
On land, you use a car.
Yes.
On water, you use a ship.
Yes.
They're different. And, I mean, on things like this, you know, you just have to use wave theory in all respects, including, you know, total refraction, lateral waves. It gets very complicated, where you have to, I mean, the only guiding thing is wave theory.
No, sir.
But you can't think.
No, sir. That's incorrect, sir.
Convince you that there's an alternate.
That this is the way to do it.
Well, but this, I mean...
At this level, it looks like wave theory. You forget that you're computing probabilities. That's not right, according to wave theory. And we'll show you circumstances in which the wave theory doesn't work. We had one with the two boxes. If you have problems in which you have two photons, which are correlated in their properties, the wave theory is unsuccessful.
Yeah, but it doesn't help me. It only
Doesn't help you to do this, you mean?
problem as soon as I put a photon multiplier there, because that works by the
But you haven't done any problems with two photons that are correlated. That's nonlinear optics problems, for example.
No, we have a problem in
You haven't done them, therefore you don't appreciate.
They don't come my way.
Okay, so because you have a limited range of experience in which you work, you might find that some other model is sufficiently successful that you don't have to do it this way. What I'm trying to show you is a model which works, ultimately, over the entire range of experience that man has been able to find, not just over the limited range of experience for your particular experiments, okay? It has always been this way, that for a particular range of experiments, a certain idea may be a good enough approximation and complete enough because you don't do those experiments which get you into trouble with it. And then it may be much easier on the head, if you like, to use that model. It's much more easy to imagine the waves moving in space and so on. But you will, if you wanted to do a wider range of experiment, get into trouble if you perpetually thought that way. I guarantee you.
But still,
Whoa,
I mean,
that
you
sounds
started
pretty
out by
heavy.
saying that what you have today, might be changed tomorrow.
That's true, because we have no experiment.
So the current universal model
Right.
is only a temporary model.
Perhaps.
And so,
But why do I go back to your temporary model, which I know is wrong in certain circumstances?
as long as I know where to use it, where not.
That's perfectly all right, sure. But that's not what I'm lecturing about. I'm lecturing about the physical view over a wider range than your particular experiences. And so I want to tell all that we know, not some approximation which works in part of nature, okay? So that's the reason I'm
Also,
doing
there's
it.
something else which is very important, which is to prove that this sort of crazy way of looking at it reproduces all your results perfectly well, which is what you have to do when you invent a new theory.
We have to show that it produces some results that he doesn't know about, too, such as the two photon correlations that were those boxes in the beginning.
Well, then you get into line spectra and all kinds of things that the wave theory falls on.
There's lots of difficulties with it. It's got mostly to do with probabilities. You can't interpret the wave as a probability. And all it really is that the wave is interpreted as a probability instead of as an intensity in first approximation with one photon. When there are photon correlations, it has to be done with arrows. Okay?
A little stretch.
Sure.
Is that okay now?
Well, of course.
Yeah, I like a stretch. Yeah, like every staff that can possibly do that.
So you say your wave probability is C of arrows?
Yes. Right. If we have more surfaces, well, let's see, what should I describe next? We appreciate the plus. No. I would like to talk about what happens if there are more surfaces. All right? If there are more surfaces. For example, if I had a layer of glass here and then of air, much like you like to make, and then we would have another layer of, let's say, glass of a certain thickness, something like that. Maybe not the same thickness as this one. Well, let's erase the red line to make the picture a little easier. But we have thicknesses, 4 of them. Then what happens is that we would make 4 ways that the light could go, if you imagined it. You could say it goes first surface, second surface, third surface, and fourth surface. And then we would have an arrow for the first surface case, an arrow for the second. If these were different materials, they weren't both glass, they may not be the same length of arrow. Some other arrow for the third, excuse me, I made it wrong. An arrow from the first surface, an arrow from the second surface, another arrow, let's say it's bigger, let's say it's a thicker glass, different kind of glass, lead glass, so it's not 1/5, it's a little bit bigger. This is the third surface, and this might be the fourth surface. How do you put them together? You consider them, you add them, again with the word add. We use the word add, but what we mean is we find out what the net result would be of this sequence of steps. In other words, we try to find out where we would end up if we made a series of steps, this step followed by that step, followed by that step. And the easy way to do that geometrically is to draw one and then draw the next one on the end of that. That's number 2. And then number 3 on that. I didn't draw it quite at the correct angle. And then number 4. And then the net result for the probability would be the square of this length. In other words, the area of a square set on that arrowhead. That would be the answer. So when we have any numbers of surfaces, all we do is figure out the arrow corresponding to each one and tie them together by what we call addition, which is really seeing what happens if you do a sequence of steps corresponding to those arrows in succession. An interesting point about adding, which is fun, with numbers it's true that 5 plus 4 is the same as 4 plus 5, and it doesn't make any difference in what order I add them. If you play with this a little bit, you'll discover that if you make a series of steps of different lengths and angles, you'll get to exactly the same place with no matter what order you make the steps in. If you make a big step this way, followed by a small step that way, you get to here. Whereas if I made a small step that way first, and then the big step, I get to the same place. And it'll turn out, if you play a little bit, that if you tied arrows on each other's ends, but kept the same arrows, but tied them in different order, it'll come to the same answer. So this addition also has that property. It doesn't make any difference. You don't have to decide which is first and which is second when you're adding these things together, okay? You just put them together, and it'll work whichever order you choose. Now I would like to describe the language we use to describe this, right? We call the arrows, actually, a physicist calls an arrow an amplitude. He actually more completely sometimes calls a probability amplitude. All it means is a quantity, which one squared, or rather which one you find the area of the square corresponding to the arrow is a probability. The word probability amplitude is just, I could have better say probability arrow. What I mean is that you use the arrow to find the probability by figuring out how big an area of a square on it is. So these could be called probability arrows. Actually, technically, these arrows are called amplitudes. It's just another word for these arrows, right? No complication. I would like to use the word amplitude because I'm so used to it. It probably would be easier for me to say the probability arrow associated with this rather than the amplitude associated with it. But I'm used to using amplitude, and we might hear the word somewhere else, and now you'll know what it means. So what we do is this.
Amplitude, that includes angle.
Yes, the amplitude is
Not the scalar, it's the
no, it's not the area, that's the probability. The amplitude is the arrow with its angle and length, the combination. That's the amplitude. It's the full arrow. It's got two aspects, the length and the angle. That's the amplitude. Amplitude and arrow is the same, all right? Just get used to that. Now, we have discovered from our experience with the boxes and also from talking about this, that it will not work out right, and we'll get into all kinds of trouble if we would say something like this, that this particle, in the classical sense, that this photon has a certain, comes down to here. There's several ways it can get to here. It can come from this surface, or it can come from this surface. There's a certain probability to bounce from this one, and a probability for the bounce from that one. That will not. We've noticed that, because if there were a probability to bounce from the front surface and the probability to bounce from the second surface, if you added those probabilities together, you couldn't get zero, as you sometimes get for certain thicknesses, because all probabilities are always plus. So that theory, that way of describing that we say the photon probably does this or that, is much like with our boxes, that they're probably red, red, green, or green, red, red, or whatever they are before we open the box. In other words, before the photomultiplier reads, we cannot say, we do not say, that this photon either goes this way or that way or this way. But we do say, following language, it has an amplitude to go this way. It has an amplitude to go from the second surface. It has an amplitude to go from the third surface. It has an amplitude to go to the fourth surface. Then you add the amplitudes together to get the amplitude to arrive here. The amplitude to arrive here has only meaning in the sense of the probability of arriving here, which is the square of the length of the amplitude arrow. So, to say it again, every event that we want to calculate, we calculate a probability. These probabilities are always the square lengths, the area of the squares, associated with arrows, translation, associated with amplitudes. For every process, we compute an amplitude for that process. The probability of that process is the square of the amplitude, the square going on the arrow, right? The amplitude for a process which can happen in several alternative ways in your imagination is simply the sum of the amplitudes for each of the individual waves. In other words, the arrows, total arrow is the sum of the arrows for each of the waves. So that it turns out with this happy way that we can blithely go along and thinking of it happening as alternative different ways, but not in the probabilistic sense, but that in the amplitude sense. There's an amplitude for it to happen in all these ways, and we have to add those amplitudes. That permits cancellations and so forth. Arrows, when they add, can come out zero. Probabilities can't. You can't add two positive numbers, two chances, and get nothing. So, but with arrows you can. So the language we use is to say that there's amplitudes for different possibilities, and to find out whether it's actually happening, with what chance it happens, we have to, in the end, when we know the amplitude, find the square area that belongs to that amplitude, that arrow. Right?
That square area has no direction, right?
No, it's just a way of my describing just squaring the length. It's a numerical process. You don't have to draw that square, but for people who don't want to calculate, I just draw the square to indicate the bigger the square, the bigger the probability. If the arrow, and an example of that, why it's nice to draw the squares so you don't have to calculate anything, is remember this last one where we had the full maximum corresponding to this position here. Then we had an arrow this long, which was 2 units. Twice as long as the original one alone would have been. Twice as long as the first surface. If it were the first surface alone, it would have been so big, but it's not, it's twice as big. Now if we draw a square on it, and compare that to the square from the first surface alone, with a little bit of drawing, we can see that there's 4 of these squares, and therefore it's 4 times more. So for individuals who can't square numbers easily in their head, I've shown you that the double arrow has 4 times the probability than the single arrow, because the probability is the area of the squares. And so therefore, when we had the 2 surfaces so lined up that their arrows were in what we call in phase, that is in the same direction. Phase and direction, or angle of the arrow, is the same thing, just other word. When they're in the same phase, and they go that way, and they add together, then the probability is 4 times as big as one would have been alone. That's why 16% is what happens rather than 4%. All right? I was just drawing squares to help you to calculate squares. If you're used to multiplying numbers together, then you can just take the length of the arrow and multiply it by itself. In fact, I did that in this case over here. I forgot that I had invented this square to save me from having to multiply numbers. So I've got it down to the point of counting beans to the last degree, that you don't even have to multiply numbers in order to find the answers to this. It's a geometrical square. Okay? So that's the language we find ourselves using. We talk about amplitudes for possibilities. If I were talking about those 2 boxes in a more sophisticated way, I'd say there's a certain amplitude that the combination is red, green, green. Another amplitude that it's red, red, red. And I talk about adding those 2 possibilities, not by adding their chances, but by adding the amplitudes for each, those 2 arrows together. And that's the way I can get funny numbers that are not what you'd think you'd get with probability. Yes?
I think maybe what John was worried about a little bit in that earlier question
Yes.
is just that a probability is always a number between 0
And 1.
Between 0 and 1.
Yes.
And it looks like you'd have an arrow of any size and you square it and get any number.
Actually, you can't. These arrows are small enough that when you put them together, you can't get any number.
Yeah.
It's true. You mean if I made enough surfaces and had them lined up perfectly, you say, why not? Look, there's 0.5 for each surface. So let's make 10 surfaces. And let's put their position such that the timing is such that all these arrows line up. Then we'll get more than 1. The thing will be a probability more than 1. That's because I made a mistake or an approximation. I disregarded the situation, the fact, and I'll explain later more correctly how to do this right. I made a little bit of an approximation. I assumed that what happened on the back surface, that the light that got to the back surface was not already affected by the front surface and so on. We'll come back and explain how to straighten that out later, okay? In fact, I can do it now. Why not? Where I've simplified this discussion, and we can even see that in 2 surfaces I've simplified it, there's a slightly more complicated. I've left some stuff out in order to get the rules straight by making it simpler for you, by leaving something out. What I've left out is this. Not quite prepared. I have to go back to my room and check numbers and see how to explain it quickly, but I'm going to explain the problem. There's several ways that this light could get here. One of the ways is to go to this surface and come to here. That's one end. Another way is to go to this surface and come to here. But there's still another way. Can you imagine what it is? Yes. It could go to this surface, then to that surface, then to this surface, and then back to here. That's another little arrow that has to be added on. This is incomplete. There's not just two. There's another one. It turns out that one's particularly small. I'll explain the rules for finding those later. They get very small. They're very small. We could, of course, come down, hit here, go up here, go up here, go back, and go back, and then go up here. So there's a lot of little pieces that I left out. Now, when you have these 5 surfaces in which you're trying to line that up and make it very much bigger, then all those other new possibilities are also enhanced in such a way that they add up and screw you up so that you don't get more than 100%. The details will be presented next time when I have a chance to lay it out in a simple way. I don't want to confuse it by screwing up while I'm trying to explain it, okay? But there are these other possibilities which we've neglected in this discussion. Yes, I would like to do one other phenomenon that you're familiar with by arrows instead of the standard way of doing it. This phenomenon will bother you still more because it's much easier to understand by common sense. Nevertheless, the problem is this. With these rules of arrows, which is something new, how can we understand everything that we understood before in a different way? In other words, when we have a system of rules, we can't use one rule for one case and another rule for another case. We'd like to see how this kind of rule analysis works always, even though there might be an easy way to guess the answer from a different point of view. I want to show how this consistent point of view produces all results. And the results I'm going to show now, next, are very simple ones, which you would certainly believe and see in a much simpler way. So why do this? Why we do this, I'm trying to show you how this particular theory is the universal theory under everything. It'll produce even the phenomena you're used to, as well as esoteric ones. It does them all. The phenomena you're used to can be explained much more easily by some model, but that model will not hold up if we extend the array of phenomena we want to observe. This, however, holds up over the entire range, familiar and unfamiliar. So, the familiar one that I want to discuss is reflection of light from a mirror. And that's easy. So, we have here a mirror. In fact, this mirror could have been one surface of glass, if you want, right? That's a partial mirror, but it doesn't make any difference. So let's take a mirror, and here's the mirror surface. If I shine light straight down and back, we've already talked about an amplitude that it gets sent back, which is 1/5 for the surface of glass. And if you make it a good mirror, that 1/5 gets to be 1 from the surface. If you make it perfect, it would be 1, yes.
That's a theoretical mirror.
Yes. Now, if, however, the thing I want to change now is instead of thinking of the light and the situation and the geometry only up and down, I want to think this is a really two-dimensional world. Our source is over here, and our detector is over here. All right? And now I'm going to try to calculate the chance of getting light over there. But what I want ultimately to understand is what everybody knows, is that the light goes, then hits the mirror and goes to there such that the angles are equal. It goes, the light goes this way and then comes to here such the angles are equal. I never made a rule about angles being equal. I talked about arrows. Where the hell are the angles equal? Now I show you, all right? Magic way in which the arrows produce this result. You know what I'm talking about. If for this example, if your eye was here, you would see this in the mirror at this location. Actually, it would appear to be back here, the optical effect. It appears to be, an image appears over here, which is simply the same distance behind the mirror as the actual object is in front. So the eye looking at it sees it here as if the light came from here, but actually it comes from there. And if you figure it out, this angle equals this. Reason is, by the way, if you remember elementary geometry, that if you were to draw it to that image, not the reason is, but imaging works because, you see, when you have elementary geometry, these two lines make the same angle coming this way as they do going out the other way. This angle here is the same as that. But because of the way I've drawn this symmetrically, this angle here is also the same as that. And these two are equal. That's the standard description. It doesn't look very equal on my drawings, but that's supposed to be equal. Now I would like to explain why that is, okay, from this point of view of arrows. So I'm going to try to discuss this. And here's how you say, why does it go only there? Well, it's very amusing and very interesting to see how it works. I'm going to do it this way. I'm going to suppose the light goes straight through the air. We'll later discover even that can be explained. We've been assuming that, but we'll take that. But let's suppose we don't know that light has to be reflected here. And we would just say, for purposes of analysis, that we divide this mirror into very tiny sections, little pieces of mirror, okay? Bip, 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 just to think. The smaller you do it, the more accurate your result will be. This is small enough for us. And it goes on, although I don't want to draw. All right. So I want to think of this. I'm going to say, and it's going to be right, what I'm going to say, that actually there's an amplitude to arrive here. I'm going to calculate the amplitude that a photon arrives, which you can do in many ways. One way that the photon may have gotten there is to go down this way and go across to here. Right? Not very likely. I know it's equal angle. Shut up. It's possible. It doesn't know anything about that. Another way, I'll draw in purple so you can see it's another way. It could have gone to another spot and gone to there. It's still what the right thing. It could go to still another spot. I love these colors. Let's say it goes to the spot way over here and goes to the photomultiplier. Yeah, right. And by the way, there's still another way it could go. It could go straight to here without going to the mirror at all. That produces very funny effects, as a matter of fact, but we'll put a wall in here or something to stop that light. So let's imagine that this is specially built, that there's a wall in here so that we don't have to consider the light that doesn't hit the mirror, all right? This, of course, was one of those spots. Because of my laziness, I haven't drawn enough of these dots in here. Now,
Is this a point source?
yeah, and a point, it's a very tiny detector. There is the one we're looking for. Let's say this is the one of equal angles. That's in there too. That's this one. All different, well, I'm sorry, I shouldn't have bent that line. Okay, let's say that there's this one. Let's put the right one, we'll suppose. Okay? But every one of them is there, and every one contributes an amplitude, a small amplitude because it's a very tiny section, a little tiny arrow. And I'm going to add all the arrows together, and I'm going to show you, like a magician, how it works, how the mirror works. I'm going to add every one of these cases. Each is equal. Each one of these things is the same width, and although the distances are varying somewhat, they're almost equal in their contributions. Every one of these is equally important. So let's start to draw the arrow. I draw the arrow for this one, a tiny little arrow, at some particular crazy angle that depends upon the total time to go from here to here. In fact, just for fun, well, no, it's too silly to draw the blue one and the purple one and the black one as arrows. But, okay, the blue one is going to look like this, see, the arrow contribution from the blue one. Now the purple one has about the same width and some slight difference in distances, and I'll give you the rules for those arrows, but it comes out almost the same size. However, the time is very different, because the time it takes to go from here to here and the time it takes to go from here to here are not the same, because if you'll count, well, let's take it's perfectly clear that this distance total is longer than that distance, for instance. They're different distances. Therefore, they're different times. So all these arrows that I'm going to draw, the purple one, the black one, and the green one, they all correspond to arrows in some crazy directions, depending upon the time, all right? And I have to put them all on top of each other. Not just these. I also have to put all the ones in between. Okay, so it's a big calculation, adding thousands of arrows together by tying them one to the other. Remember how to do it. You make the succession of steps. Then, okay, now we're going to do that. I hope I have time. Yes, I do have time. We're going to do that. In order to do that, we have to know at what angle to turn the arrows. That angle is the total time taken to go. And the total time taken to go is, of course, the distance divided by the speed of light. And so what I need for each of the arrows is an arrow associated with this spot, this spot, this spot, this spot, this spot, and so on. In order to figure out at what angle to draw it, I have to know how long it takes or how far it is. Okay? So let me make a little diagram or a plot, a graph of how much distance it is, or time. It's the same for us because it's all through air. And it's going this way. And this axis is supposed to really be exactly corresponding to each one of these. In other words, for this particular spot here, I calculate the distance is there. For this particular spot here, I should do it in purple, but it takes too long to keep picking up the different colors. So this one here, turns out is somewhat shorter. This one here, maybe even shorter. After a while, it's getting long again. As a matter of fact, you can appreciate the one that goes straight down, and if this is there's some kind of symmetry, if I happen to have them at the same level, that there'd be some symmetry, would go up again. At any rate, the distances, or the time, which is equivalent, because we haven't said what the scale is on the axis, there's a curve which goes down to some lowest value and goes up. Unlike my drawing, they should have gone through these dots, so I should have put those dots there and moved the dots. But you know what this means then, and these are a whole lot of little dots corresponding to the time for each of these places. And there's some place in the middle there somewhere where the time is shortest, and then it begins to increase again. Are there any questions about what that curve is and why it looks that way? Because it's important to appreciate that.
I'm not sure where you're getting the distances from. What does that first point
Good.
correspond to?
This point corresponds simply to the total of this length and that length. The total distance to go from here to here and from here to here.
So it's a summation of...
All it is a summation of those two lines. As a matter of fact, it could be constructed geometrically that way. You can go home tonight and draw a horizontal and 2 points, and on the horizontal lay out dots and draw these things and then lay them out, measure them, and then measure this height here should be equal to the total of these two blues. Actually, I don't have room to draw, so the scale is different. Okay? And you'll discover that there's some distance at which the time is shortest, and then it goes up again. The only thing that really counts in this curve for us are the dots, one corresponding to each one of these little sections. Of course, we can make the sections very fine, have lots and lots of dots if you want to. Now,
Is that a little piece of that other curve that you did, the big up and down curve?
no, this is entirely different because we're plotting something else. We're plotting the distance to go at different points, and that's not to do with the intensity of light from the other. It's a different problem, and it's a different quantity, and so the axis here is position of the mirror rather than wavelength, and it's entirely different, okay? Okay, now with that, this tells us how to draw our arrows, yes? Because it tells us at what angle to draw the arrows. So I'm going to call these number 1, number 2, number 3, number 4, number 5, number 6, and so forth, and I'm going to draw the arrows corresponding to each one. So I don't know where it comes out, but number 1, say, comes out this way. And number 2 is a different time, quite a different time. Maybe less time, so I at least should do that right. That's number 1. You might not like it because the arrows are small, but I better make them small, I get in trouble. Number 2 is at a different time. Number 3 is still less time. Less time means not turned as much. Number 4 is less time, and I haven't looked over here exactly how far I have to go. But after a while, less time, after a while the arrows begin to go more or less in the same direction. Why? Because when I'm down near the bottom here, all the times are nearly the same. Therefore, all those arrows, whatever their angle, they're all the same for a while. So if this was called 10, it isn't right, 11 actually, and this is 12, 13, 14, and so on, then this would be arrow 12, 11, 13, 14, almost the same. But after a while, I begin to climb up here. My angles begin to increase again. That is, they get parallel to the old ones. See, so they begin to turn over this way. And then as I begin to climb up this hill, as I change from dot to dot, the times change more and more each time, so that the arrows go more and more cockeyed relative to each other, more and more rapidly around that way. And they're just really millions of them all going crazy. I mean, when you're climbing very fast up here, this arrow is this way, this arrow is this way, this arrow is this way, this one is this way. They're all different angles, so it's a big smear. And it was, in fact, if I went all the way back there, the smear at the beginning here. So I wonder if you can understand this, why I got that. I put together a lot of arrows whose angles, let's start at the bottom and go up this way and back that way. As we go up, we add the arrows almost the same angle, and then we begin to increase them faster and faster and make a little whirl. Back to the other way, it was symmetrical. I should have been adding arrows which are nearly the same direction, but all different angles and make a little swirl. That makes this kind of a curve, beautiful curve if done very carefully, called Cornu's spiral. Swirl and long swirl. Now, what's the answer to the probability of reflection? Jesus, I forgot we were trying to find that. Oh yes, so we started with the first arrow, which is somewhere down in the swirl down here, and find out where the last arrow was. Remember what the net result of all the steps. In other words, we're playing a game. You could almost do it in a room. You say to people, all right, make a step, turn this angle, turn this angle, turn left, turn left, turn left. Now we're going to turn, I'll turn more the other way, and so forth, and they make this path. We want to know where they end up. And they would end up over here, which is a sizable arrow, and represents a good probability. So what? So we found that we do get counts. In other words, the mirror works. That's for sure. But what's all this business about equal angles? Where did that come from? The only reason this arrow is long is because we have a succession of the pieces that are almost in the same direction. The parts in which the things are not the same direction don't make much difference. If we would cut the mirror off, throw it away, throw this part of the mirror away. I should have really, yes, it's better at the other end. It's the way it happened. Throw this part of the mirror away. Then that means that all the arrows from here on out are removed. They're not there because the mirror isn't there. Then this length is almost the same. In other words, we don't need that part of the mirror to get the reflection. Likewise, we don't need the part of the mirror on the other side where the things are changing fast. The only part of the mirror that we really need to get the reflection, we could throw the rest away, is just the section in which the times are not changing much. All right? Now, it's a geometrical thing that you have to figure out. Where is that? Where is the place when you move this around a little bit, it doesn't change the timing much? It turns out that's the place of equal angle. I'll show you why in a moment.
But if you decrease the size of the mirror sufficiently,
Yes.
then you get in trouble.
Yes. And then if you make the mirror too small, then it doesn't really work very well. Furthermore, it doesn't know about angles at all, because if you put this in any other position, you get that one little arrow, and it's the same size no matter where you put it. Any mirror, it loses its knowledge that it's supposed to be angles equal. You only get angle of incidence equal angle of reflection with a mirror sufficiently large. That's rather small in practice. And so ordinary mirrors, you think everything is all right. Yes.
Seems to me you can test this theory.
Yes.
Make sure that this thing of adding up all these rows is correct.
Yes.
By very carefully taking all little segments.
You could. Why don't we cheat this? All right, good.
And get those things back.
I know it's 12 o'clock, but because he brought this up, and it's very interesting, let me continue a little bit longer. Okay. His suggests this. This sounds insane, what I just said. I mean, I'll put it my own way, but I'll come back. All this is canceling itself out. It's not doing anything. You don't need this part of the mirror. What I say from this crazy theory that I'm talking about is really kind of nutsy. I have a whole part of the mirror, which I compute a whole lot of little arrows, and it's happening, and the net result is nothing happens from that part of the mirror at all. It must be a myth that this stuff is happening. Why do I have to include all that junk? Right? Why do I have to add all those arrows which cancel out? They don't add up to anything anyway. I don't believe it. I don't believe that that really is reflected. But he says we're going to check it by a trick. The trick is the following. I think his idea is the following. Something like this. When you make the arrows, let's say down around in here, some of them pointing this way, and some of them are pointing this way, and some of them are pointing that way. For example, as we go along, from one point might be this way, the next point this way, the next point that way, the next point that way, and so on, right? Why? And then it comes around and goes around again this way, and it doesn't get anywhere. So he says, remove the mirror in just those places
where the contributions would be going backwards. In other words, throw away the ones that are going backwards. Just add the ones that are going forward. As soon as an angle gets like they're getting ready to go backwards, erase the mirror, take them out.
Take out the middle too, also. You just take out the middle.
No, just take those out in a sense, where it's going the wrong angle. And then these are not there. So it doesn't come back. They're removed. Then they begin to be the right direction again as they're coming around. Let those be back in, so we go this way for a while. As soon as it starts to go this way, remove them. How? By just erasing the mirror. What would happen if I carefully figured out which ones were giving arrows generally in this direction? In that general direction, if they have a component, so to speak, in that direction, the step is, although not precisely the direction I want, is less forward, I allow it. And when I calculate one that's pointing the wrong way, I simply erase the mirror, make a hole in the mirror in certain places, holes. Well, then there's a place you allow it, and there's a hole, and there's allowed, and there's holes. Well, the holes are made so that this will never back up. And then the result would be that we would get a very nice thing, and we would go blip, 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 blip. These are the sums of these arrows. And then it would go straight for a while, and then go blip, 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 blip. And we get a very strong and beautiful reflection. Even stronger than if the whole mirror's there. It would appear. And that works. You can do that, and it works. In fact, as he said, you can even do this so well that you can forget the whole, this part of the mirror. That's a good way to think of it. Let me take 2 more minutes and explain the same idea over again, but even more dramatically.
Take your time.
Yeah, let's suppose that somebody said, forget this mirror, he's not even there. What happens then? I have a mirror that's only so long, okay? I go back and I analyze, thanks, I forgot to do it that way. That's the nicest way to do it. I have a mirror only so long. Then in that mirror, all the arrows are just like this. They're adding, and then they go around fast. Everyone is different, because what I'm done is I'm only used this part of the curve. I never got to the place where they're all the same direction. So they're all different directions. You're going all over the place. So we get this thing going around, going around, going around, and it doesn't get very far from the beginning. The biggest it can get from the beginning is some short distance across here. There's not very much reflection from that. It all cancels out. Now we use his trick, that when the arrows are pointing the wrong way, in other words, as we make a contribution, we see it's this way, this way, this way, as we go along from one spot to the next. As soon as the mirror arrows start going the wrong way, like backwards, we erase the mirror. So what we end up with is a series of only the positive arrows, and are therefore able to get a reflection from the mirror which would ordinarily not reflect. If the whole mirror was there, it would not come any light, very little light would come there, because it cancels out. But if I erase the mirror in exactly the right places, let's take less mirror.
Less is more.
There, and to your sudden delight, there's a lot of light there. And that demonstrates that these parts really were having an amplitude to send light there. And the other parts were also had an amplitude to send light there, but it was opposite, and they were canceling. And this cancellation is not a myth, because by taking out half of it, you get a big effect. This device is called a grating. It's made the usual way of making it, instead of making it with the little pieces of mirror, although it could be made that way, just to make lines or slices on a plane. You may have seen these gratings. They used to use them for in cars or something. Sometimes you see colored, white color on a sign, and as you turn, it changes colors and stuff. That's a grating. What happens accidentally is this. I have to, when I cut these things out, I have to figure out the time exactly to know which arrows go backwards. And that depends upon how much a difference in time means how much rotation. That depends on the color of the light. So if I cut this out so it works for red light, it won't work at this angle for blue light. It only works for the red light. It doesn't reflect blue light very well. However, it turns out accidentally that the mathematical places to make these cuts for red light, for this position of the source and this position of the reflector, turns out to be correct, or nearly correct. For blue light, however, if the source was over there, the timings will change, but it still fits together. And the detector here, or vice versa, just changing the ends. When you turn it, it gives different color lights, it's the same gradient. That's a little complication, but the main point is that this idea that there's a lot of effects in regions where you wouldn't expect them, like in parts of the mirror where angle of incidence is not equal to angle of refraction, is really right, because if I erase parts of the mirror there, I can get an enormous reflection from places where the angle of incidence is no longer at all equal to the angle of reflection. All right?
No matter how familiar one gets with that, there's always a bit of awe about that.
Yes, because the awe, it does not be awe if it were waves, you see. But when you realize that what you're doing is counting photons one at a time, and they decide to come or not come, you just figure this way. With this section of mirrors in here, they're coming. How in the hell, by putting more mirror in there, can I stop them from coming? But that's what happens. You get counts with the holes, try to fill up the hole, and you get no counts. Say, what's that doing? And furthermore, if you have that little thing, suppose you had a little mirror section, the pieces that you took out, you put on another glass plate. So you could, so to speak, bring them up and take them away. When you take them away first, you get a lot of light. Lots of photons are coming. Bring them up, it would be easier for the photons. There's more places to reflect, and nothing comes. Then take away the blacks and leave just the greens, and you get lots of light. Both together, nothing. How does that magic work? The blacks making an arrow this way. The greens were all contributing this way. When I have them both, the net arrow is nothing. Either one is something. Either one alone, but both is nothing. That works fine with amplitudes, but to think logically about probabilities, it makes it very difficult, because you usually think if those would do it and the greens would do it, and you put them both there, they'll do it even better. So we can add amplitudes instead of adding probabilities. That is illegal, but adding probabilities is the wrong way to do it. You have to add the hours first and then make the square. Why? I don't know. Nature works that way.
Again, just like I turn blue to black, I'll turn red to orange. I'm going to add the red ones. It's a new problem. He moved the photomultiplier on me, and I'm doing it over. So I make this step, and then I make this step. Okay? And then I get the final result, which we'll draw in purple, that corresponds to the other green one there. And it looks like it's the same size, doesn't it? Maybe I cheated, I'm good at drawing. But it is exactly the same size, because if you think about it a little while, since you turn this arrow by a certain extra angle, and this one by the same amount extra, because when you move the photomultiplier, the extra time is the same for both, the extra time. So the extra turn is the same for both. It's the same as just turning both arrows together, which is simply turning this diagram. But turning this thing doesn't change its length. And the probability that we're calculating depends only on the length. It's the square of the length. It doesn't depend on the direction.
Can't you get that directly from the glass thickness? From the glass to the glass?
Absolutely. You mean that this angle here, this delay? Yes, yes, and we're going to do that right now. And that's exactly right. That's why you don't need the accurate measurement that you were talking about. You don't really need that distance to get this probability, because only the thickness of the glass is important in computing the length of this arrow. The direction of this arrow does in fact depend upon exactly where the end of the glass is here instead of where it was before. What happens? The amplitude, well, I mean the arrows are called amplitudes, so I may sometimes say amplitude instead of arrow. It's just a word, right? We can have any word we want, like it says in Lewis and Carroll. Lewis Carroll, I mean. The reflection from the amplitude corresponding to reflection from the first surface is this arrow turned by the distance to the photomultiplier, which is that. Changing the position of the second surface has no effect on that arrow or that amplitude. Instead, however, the one which went down to the new surface and back is changed. Why? because it has to go further now. And in going further, it will be turned more. So it will be in this position instead of where it was before. This corresponds to turned more because it's thicker. This is the one that's thicker. All right? Now we have to put these two arrows together, and I'll do that over here. The black one from the old one, which is the same as it was before, straight up and down. That happened accidentally for my drawing. And then this red one, which is now, I'll draw in red again. I don't want to change all the colors all the time. Out this way more. The photomultiplier is, but it doesn't affect the probability that you'll get a count, because the count is measured by the length of this arrow squared. Right?
So it's the scalar, not the vector.
No, because I need this. Sometimes I might have three surfaces and I may not have a photomultiplier there, but when I get there I have another surface that a light reflects from and so on, so let me have it with arrows. But when you finally want the probability for something, then at the end you square the arrow. For this application, it's the same answer here as here. Okay? But if I had, instead of putting a photomultiplier there, I had put another surface there, then the exact location of it becomes very important. Okay? I had another reflection with another photomultiplier somewhere else. It would be a different problem. But let's just do this easy problem first. Let me explain why this result would occur if these rules were right. Why, if we count the beans by this way, we get this result. Let me show you, all right? He's already seen it, as a matter of fact, from his questions. Suppose that we would do the problem over again, not this time moving the photomultiplier, which was, we found out was an effect, didn't change anything. So I'm going to erase the red and orange to get space. I'm now going to ask you to think of another circumstance in which I change the thickness of the glass by increasing it, let us say, a little bit. So I do the experiment over again, and now my red and orange and all that's going to correspond to thicker glass. To make it very clear, I was going to do it over again in which the square of this arrow determines the probability of reflection. I have to have erased the blackboard because I haven't got room. So I'm reconstructing here on a smaller scale a diagram that we had made earlier, which was the reflection as a function of thickness, which I'm trying to explain. And this is up to 16%, remember? Averaged 8% and started at 0. Now let me explain why it's true, if I follow these dippy rules.
This must require an incredible accuracy of measurement.
Not particularly. Not this one.
I mean, timing here.
Oh, no, but you see the timing is automatically taken care of by just the distances. The timing is very short. But
Measuring the distance.
well, we have to have the distances good, yes. But you see, if this is put in a fixed position, it's a definite distance, whatever it is. We don't actually have to know exactly how this is turned. We have to know the relative turn of this and that. That's a nice point. Suppose that I made a mistake in that distance. Well, I moved the photomultiplier a little bit further away. Then this arrow here, the red's going to indicate what I would calculate if I had a little further away the photomultiplier. Then this arrow would have turned a little further, right? And this arrow would have turned a little further, always in the same direction. Yes? And now I want to add these two together, which I will do for these two ways. Finally, I must tell you what the arrow is for the net result. When things can happen in alternative ways, you do what we call add the arrows, and it doesn't mean anything. How do you add not arrows? I know how to add numbers. How do you add arrows? The rule for adding arrows is the following. You simply put one arrowhead on the tail of the other. If I wanted to add these two arrows, I would do it as follows. This is the first arrow. Let's say that's 1 and that's 2. That's the first arrow. And then I just draw the second arrow off from the first one. Okay? It's exactly parallel. So drawing the same, but it's centered, is moved to there, right? You tie one onto the other, head to tail. And the result is supposed to be the sum. The adding is this net arrow that you would get from where you started to where you ended. A way of thinking of it that's rather nice is to think of each arrow as indicating the direction of a step to be taken. We take a step on this plane this way, and then we take a step that way, and we say, where did we actually move? We could have done it all in one step, this one. So this is the one step which is equivalent to the succession of the other steps. Adding means putting together steps, thinking of these arrows as steps that you do in succession. This added arrow is the final result for the chance of a reflection.